here's some of the tools you can use to answer this question. The original function has a derivative of x squared minus 1. And if we want to, and the second derivative, by the way, is 2x. If we want to find the critical numbers, that's the place where the first derivative is equal to 0. And so there are your critical numbers right there, plus or minus 1. We can employ the first derivative test to find out where the first derivative is positive and negative in the intervals created by the critical numbers. It's supposed to be a 1. And that will tell us the intervals on which the original function is increasing or decreasing. So for example, here's the critical numbers, -1 and 1 on a number line. And then pick a test number in each interval, like to the left of -1, what's f prime of -2? If you picture putting a -2 in here into the first derivative, you can see you get a positive number, which tells you that the tangent lines have a positive slope, which tells you the original function is increasing. In the interval from -1 to 1, pick a test number, like the number 0. What's f prime of 0? It's -1 actually. So that tells you the original function is decreasing in the interval from -1 to 1. And similar to the right of 1, the first derivative is positive. So the original function is increasing everywhere to the right of 1. And by the way, that matches our end behavior that we can determine just by looking at the original function. The leading coefficient is positive. The degree is odd. So when x approaches -infinity, we are approaching negative numbers. So that means to the left, the behavior is down. To the right, the behavior is up. And that means since we went from increasing to decreasing at -1, there's a relative maximum at -1, f of -1. And there it is right there. Since we went from decreasing to increasing where x is 1, there's a relative minimum at 1, f of 1. And there's the relative minimum. We could also use the second derivative test if we wanted to identify relative maximums and minimums. If if we put the critical numbers into the second derivative, we find that f double prime of -1 is a negative number, because -1 into 2x gives us a -2. Therefore, at -1, f of -1, we have a relative maximum. The way you can think of this is that when the first derivative, or when the second derivative is negative, the curve or the original function is concave downward. Think of a frown, negative. And so there's a relative maximum at -1. And similarly, f double prime of 1 is positive, therefore there's a relative minimum. Think of this as concave up, smiley face, positive. So this has to be a relative minimum. I call this finding hypercritical numbers. There's not many textbooks that use that phrase anymore, but old textbooks used to say where the second derivative is equal to 0. We've got hypercritical numbers, and if you do want to do a test for concavity, put 0 on a little number line, determine the sign of f double prime in each interval created by that hypercritical number. And when f double prime is negative, which it is to the left of 0, the original function is concave down. Again, think of negative as a frown, positive as a smiley face. Concave up. Since we changed from concave down to concave up, there's a point of inflection at 0, f of 0. There's the point of inflection. And if you really want to get you can figure out what this root is approximately by using Newton's law, Newton's method, which is what's depicted over here. So this root, using Newton's method, is about negative 2.104. So just to the left of negative 2, we cross the x-axis. And so that helps you sketch the graph. There you go. Hope that helped. If you have any questions, post a comment.